So let's say if we view an educated person as someone who understands that you need to have more equations than unknown, then pretty much anybody who could consider themselves educated would say, well, you can't solve that problem. On the other hand, science does progress, and there must be some way that that happens. And sparsity is one reason that you're able to resolve such problems in practice. By sparsity, I mean that we can suppose that only a small fraction of potential predictors really contribute to the response. So that we may have measured in just out of laziness many more things than ever could really be involved with the phenomenon, and there's maybe only a small fraction that actually contribute. So there's P potential predictors, but actually only K actual predictors. And what's sort of behind a lot of modeling exercises in empirical science is the idea that K is smaller than N and N is smaller than P. George Bach, sometimes in the 1980s, laid out the hypothesis of effect sparsity in factorial experiments, where the number of potential predictors is sort of the number of raw predictor variables plus the complete set of all their interactions, which is polynomials involving all of those things. And it was clear at the time that obviously there, you just wouldn't never get enough data to figure out everything conceivable. But maybe some of the higher order interactions were non-zero and most of the others were zero. So then you had the hypothesis of effect sparsity in those settings. Anyway, the sparsity assumption is implicit or explicit in many fields. When people talk about they want the simplest model, they talk about using Occam's razor, they talk about using data compression, other things. They're in some way appealing to sparsity either in an explicit or implicit form. Classically, model selection is the natural thing to do when you have a situation of sparsity. Out of the many potential predictors, you select subsets of what you think are the actual predictors. So let's say probably the oldest idea is what's sometimes called screening regressions, or I think Bryman and Friedman in the early 80s gave it that name. And I would say that's probably the first thing I ever did when I was an undergraduate working as a TA on an environmental monitoring project. You perform all univariate regressions. And you regress a response on every individual predictor, and then just look for the individual predictors that by themselves have significant t-values, where significance has to maybe be thought of carefully since you're doing a lot of different tests. And then you fit a subset model using the selected predictors at that stage. I was then taught that screening regressions wasn't such a good idea because there were interactions between variables, and the orthogonalization that ought to be done was being ignored. And so there's a technique called forward stepwise regression, which was the second thing I ever did as a 17-year-old. Start with an empty model, then repeat the following loop until you decided that there's no significance remaining. Namely, with your given model, look at adding one new predictor, say by the criterion of choosing the individual predictor not yet in the model, which seems to be most statistically significant. Expand the model by that term and then repeat. So forward stepwise regression with various ways of assessing significance and maybe variations on whether using a t-test to decide that or some other method is heavily used throughout science and technology, and probably most model building is done this way. Now, there's more computationally intensive methods. For a long time, people have known that you could enumerate all possible subset models and optimize some trade-off between fit and complexity. And coming out of statistical physics, there's ideas that you could randomly sample from all possible subset models using a kind of Bayesian prior that's perhaps based on complexity. Then there are very popular computationally tractable methods like lasso and LARS that optimize things that are not as difficult and combinatorially oriented as what you would have with all subsets regression, but instead can be affected using convex optimization or even just straightforward linear algebra. Okay, so to formalize things a little bit, suppose we have n observations and p sub n variables, so we think in terms of a triangular array setting, a whole family of problems. And the problem size is going to infinity, so we're not having such a low sample size. We're having a relatively large sample size, relatively large number of variables, and I'll use the L0 norm as a notation for the number of non-zeros in the predictor vector, in the prediction coefficient vector. And I'll talk about this proportional growth setting where we let all three variables tend to limits in appropriately dimension normalized setting. And these limits have interpretations. So rho is a measure of sparsity. That is, if it's small, then we have a very high degree of sparsity in the model. And delta is a measure of indeterminacy. If delta is small, then we have a very high degree of indeterminacy of the underlying linear equations. So there's a slight inversion in the sense of the words, but I hope people won't get misled. So rho and delta will be state variables in the asymptotics that we want to develop. Here's a little experiment that was run by Vicki Stodden, who got her thesis at Stanford. I was her advisor. Let's consider a situation where there's 200 potential predictors, and we take a number of observations that's set up to obey this variable delta, and a number of true predictors set up to cohere with this variable rho. And we're going to go across all delta and rho in the unit square and conduct an experiment. In each case, we're going to have Gaussian white noise in the observations and choose the non-zero coefficients to be uniform distributed. We'll do forward stepwise regression and stop with false discovery rate at 1/2, which is a rule that we could discuss, but it's just a particular way of saying when we think the model's big enough and there's not much reason to proceed. So what she found is the following. What we're plotting here is the shaded attribute is the predictive mean squared error for this stepwise false discovery rate procedure. And as you can see, there's a deep blue region and a red region. The axis down here is the indeterminacy. So this is just barely determined, and this is increasingly underdetermined as we move over here. What we see on that axis going up is sparsity. So down here we're very sparse, and up at the top we're fully dense. And what you see is that along any given amount of determinacy, as you increase the sparsity, you get basically something blue, then all of a sudden it jumps to red. And because of what the shaded attribute is saying, is that effectively you're making relatively small errors in predicting the phenomenon. This is a prediction, future prediction. It's not residual sum of squares or something, but how well are you able to predict using those coefficients on independent replications? The coefficients that you're having really work, boom, and then they're absolutely useless. So there's a sudden transition as you sort of cross a cliff and fall off of it. And so model selection, according to this stepwise regression, works until it doesn't work. Okay, now there's a curve on there I'm going to talk about, and we'll go into great detail about it, but that's calculated using high dimensional geometry in an apparently completely unrelated problem. And it's quite suggestive that the main features of that curve and the features of this experiment agree. Okay, so some hypotheses that you might be suggested to you by the graph that I just showed is that there's some phase transition in this phase diagram. There's a good phase where forward stepwise regression works. There's a bad phase where it's useless. Well, you won't know that it's useless, but it is useless. And there's some boundary between those, which is a curve that's interior to the unit square. And then maybe a sharper hypothesis is that funny curve, which we'll define later symbolically, is exactly some boundary. Okay. It turns out that once you get into this frame of mind, you can see phase transitions like this all over the place. That is, you set up a model where you have this sparsity, where you take a triangular array, you let things go off to infinity, where there's well-defined ratios of the kind of the system size to the number of unknowns and the number of valid predictors. And you observe that there are phase transitions for other algorithms, there's phase transitions for other properties, and actually there's so much that one could say about this that I've had to kind of brutally select, and I'll have to omit many of them. But for example, if we did forward stepwise regression and changed the stopping rule, we could get phase transitions that just wouldn't be at the same place, and in general they'd be lower. And as we'll see later, screening regressions, that very simple thing that I first learned about at age 17 or whatever, that also has phase transitions, which we'll talk about. And the real world meaning of all of this is we shouldn't naively assume that sparsity is going to come to the rescue. If we're in the business of conducting working with P much bigger than N, we have to be aware that unless the true model really is sparser than a defined threshold, the model selection algorithm may give us something utterly useless. We may believe we've got something out of our algorithm, may have no out-of-sample performance. Conversely, we may be looking at some real-world phenomenon and getting no out-of-sample performance and telling ourselves, oh, nothing can be done. And it could just be because we've crossed the line, and that in the data mining exercise that we did in order to get to where we got, we crossed the line. And it could be that truly a more inspired researcher would get perfect performance, and we'll never know. Okay, are phase transitions that one observes like this with algorithms inevitable? Inevitable means nothing can avoid them. So in mathematical statistics, we have this notion of decision theory. We can study behavior of minimax risk, and later we'll talk about phase transitions in that. But in order to even build up the language for it, I think it's more important to build up some understanding of the phase transition phenomenon in some simpler cases without noise, where everything is kind of precise and final and proven and published. Okay, so I want to talk about phase transitions and L1 minimization. This is a series of papers with Jared Tanner, who's here, and you could talk to either one of us about this work. And in this particular case, I'm going to have to change notation a little bit from what we were doing before. There's not going to be noise, so we're going to change notation such that the matrix of predictors, X, that we had before is now going to be called A. It's just a matrix of the same format. I'm going to change the variable so that P becomes capital N and little n stays little n. And now the vector that was beta before is going to be called X. And the correct value, beta X0. Why am I doing this? Because since we threw away noise, this now becomes a problem basically of linear algebra, and maybe the right set of notations to be using is stuff that would be suitable in applied math, computational math. And so I don't want people to get confused with a statistics problem, although this is how you actually get what the phase transition is going to be for things in statistics. Okay, so in this setting, what we've got is an underdetermined system of equations, and this is kind of the kernel of what we were talking about in that P bigger than N problem, only now it's capital N bigger than little n. We've got a way wide matrix A. We've got this system of equations that we want to solve, and we've got to do something. In principle, we were taught in college what we ought to do is complain and say, don't do this problem. But pushing ahead, we consider the following optimization. Look for the sparse.
What does K sparse mean?
K non-zeros. So the L0 norm is at most K. Okay, so the sparsest solution is the thing that minimizes the L0 norm, the one that counts the number of non-zeros, subject to solving the system of equations. And there's another optimization problem that I'd like to consider, which is the minimal L1 solution, minimize the L1 norm subject to this constraint. And kind of a basic phenomenon which has been known for some time is that there are a wide range of cases in which the two problems have the same unique solution. So it's unambiguous what the solution is to either one of them, and they're identical. So a lot of published literature on this topic since 2001, and you know, many things could be said. But basically, there's this phenomenon that the solution to one problem is the same as the solution to another problem under certain conditions. So here's an example. We take a random matrix A, and as an example, we could let the matrix have Gaussian IID elements. Another example, we could let A be a random orthoprojector, like the first little n rows of a randomly chosen ortho matrix. In any event, we can go through and minimize the L1 norm, and then measure the discrepancy between the thing that is the true sparse solution that we generated the data with and what came out of minimizing the L1 norm. And by the way, because of the properties of the matrix, we know that if we have a certain degree of sparsity in generating one of these systems of equations, then that is actually the sparsest solution. Okay, so what you get here is a phenomenon like so. There's no error at all, or maybe machine precision error, or some completely unobservable thing. And then suddenly there's error. And the error's quite substantial, and so essentially there's a phase transition, and there's a red curve there, which is what was the black curve before. So there's something happening in this particular problem. Again, this axis is the indeterminacy. As we have more indeterminacy, this phase transition comes down. More sparsity is required. And on this axis, we have the sparsity. So you have to have at least this much sparsity. Any questions? Okay, so how do you derive that curve? It comes out of the following geometric setting. The L1 ball, which is associated, of course, with L1 optimization, is called the cross polytope by geometers, because you take a hypercross and then take its convex hull. And that's labeled Cn. So suppose we take the standard cross polytope in this high dimensional space and randomly lower dimension on it. We just map it down from the high dimensional space to the lower dimensional space. So we get a new polytope, which is called the Borowski-Henk polytope. And this is a model of a random symmetric set. It's centrosymmetric about the origin because the original set is centrosymmetric. Okay. So if we took a 4D cross polytope and project it down to R2, an image in a certain viewpoint would look like this. You see that some vertices are mapped down to vertices. Some edges are mapped down to edges. Some edges are mapped down in such a way they're no longer edges because they cross inside and they're just ghost edges. If we took it and mapped down to R3, we could find examples like this where some vertices remain vertices, some vertices are mapped to the middle, some edges are mapped to the interior, so they're not edges anymore of the image, but they're just vestigial. The things that there are edges that continue to be edges. Essentially, when you lower dimension like this on a polytope, you're going to lose some faces of various dimensions. You can lose some vertices, you can lose some edges, et cetera, et cetera. Okay, so to what extent do you lose anything? How many K faces does this polytope have? So let's let these two, the N and N indices, be proportional and both very big. Then the following phenomenon happens. The number of faces of the low-dimensional object and the number of faces of the high-dimensional object are the same for sufficiently low-dimensional faces up to some point. And so there's a couple, I'm not really going to have the time to talk about this result, but I'll focus on this one here, that essentially there's almost no faces are being lost up to some level rho, where rho is k over n. So there's some, sorry, that should be k over little n. I don't know how that happened. So there's some critical point at which, some critical dimension in the size of the dimension of the face at which you start to lose faces. And that's what this blue curve is about. So if I'm interested in faces that are about 0.3 little n dimensional, then I'm above the curve here at about 0.3 capital N for the ratio, sorry, yeah, 0.3 for the ratio of little n over capital N. So up here, I'm losing faces. Below that curve, I'm not losing faces. These other curves are for related phase transitions of properties I don't have time to talk about. But for example, this one is no faces at all are lost. This one is a negligible number, fraction of faces are lost. Okay, so that's some geometric phenomenon that just happens. You randomly project a polytope, certain standard kind of polytope. You lose faces of certain dimensions under certain conditions. You don't lose them under other conditions. The relevance to underdetermined equations is indicated here. The chance that these two problems have the same solution is exactly the fraction of faces lost. And because of the phase transition phenomenon in the number of faces, there are essentially no faces lost below a certain level, and as a result, what you're going to have is that L1 and L0 have the same answer. Okay, so that upper curve here is not just about the faces loss of polytopes, but it's actually about when do L1 and L0 have the same solution. The underlying analysis of this is based on a whole bunch of high-dimensional geometry, which is fascinating, and Jared and I kind of lost ourselves in this world. But I won't go too much into it, but there's some beautiful formulas for calculating the expected number of faces for a uniform random projection of a polytope, going back to Offentronger, Schneider, and Vershik and Sporyshev. And then, some sort of exact formula for the expectation, and involves some quantities of the polytope that you're projecting called internal and external angles. So internal angles involve stuff like here's a particular face and its internal angle is the angular measure there. External angles involve we're looking in the normal space to this low dimensional space, and we're looking at things which are somehow outward pointing, and there you get an angular measure there. An important point is how you evaluate and study such integrals, and in high dimensions, all sorts of exact formulas become extremely interesting if you're a statistician. So for example, internal angles are measuring things like what's the chance that a certain number of half normals are less than a certain independent sum of normals. So hiding behind all of these things are all sorts of things having to do with the Gaussian distribution. And if you do large deviations on quantities that have to do with all sorts of things that are ultimately about Gaussian integrals, you can, for example, get asymptotic properties of these things, not just the exact formula for the curve that we've been graphing, but its behavior as you go towards very underdetermined problems. And it has the following interpretation. Say we're in the situation where we have a large number of unknowns, a relatively large number of non-zeros in our vector, but this ratio is small, so we've got a very sparse vector, and relatively speaking, how many random projections do we need so that the minimal L1 solution is exactly the correct answer that generated it? And the answer is quite sharp, and it's at n equals 2k log n over k times a 1 plus little o of 1 term. And the proof of this is just effectively that asymptotic that we just showed, that 1 over 2 log delta inverse. As an aside, there's a lot of people working on something called compressed sensing, and this shows you exactly that it's possible. It's not necessary to make capital N measurements of something where maybe only k non-zeros exist. You only need to make a small fraction of that if k is small relative to capital N. Okay, now we're emphasizing this curve, but you could wonder if it has any use outside of this one particular setting. Jared has done a lot of experiments which show that for lots and lots of different random matrix models, you get the same results. So you can consider the same experiment with different matrix ensembles. You can use fair coin tossing. You could take n rows from capital N by N Fourier matrix, n rows from capital N by N, or I should say Hadamard Gaussian matrix. You can look at uniform random projection and actually get the same curve. So here's the curve that we've been talking about, is this black one. Ignore that one for the moment. And there are some colored curves there. Those are empirical results in all these different matrix ensembles. So it turns out that there's some universality to the phenomenon that we're getting, even though it's somehow clearest that our calculations describe the Gaussian ensemble. All the different ensembles empirically give the same results. And it's quite obvious to prove that both uniform projection and Gaussian exactly follow this. So the Bernoulli, partial Fourier, partial Hadamard, those are results that are empirical. The other ones are exact. So what are some insights from this? That you can use phase diagrams. It's a way to organize your thinking. That phase transitions exist rigorously, that they're precisely known. Empirically, there's universality. Actually, there are numerous phase transitions, and I've been kind of telling you not to look at certain curves. There's lots of curves that you can calculate here. Note that the correct concepts for understanding this really integral geometry and convex polytopes, not random matrices. Although there are random matrices in the problem, you can do quite a bit with the theory of random matrices. It's not really going to expose the sharp phenomenon that's there. It'll just give you the idea that something interesting is happening. And then implicitly, the Gaussian comes in all over the place, but not because of, let's say, traditional central limit theory concerns. Okay, what I'd like to now talk about is another kind of algorithm that one could think of for model building. But again, I'm going to do it in this underdetermined equations setting and talk about phase transitions there, which can be rigorously proven. So this is a paper with Yaki Tsaig, who was my PhD student, and Ido Drori was a postdoc, and Jean-Luc is at CEU à Saclay. He's an astronomer. And it goes like this. We're again in the same setting. We have an underdetermined system of equations, and A is somehow random. And there's a sparse vector which we'd like to recover. But we don't like L1-based methods because they require a lot of sophistication to make them run reasonably fast, and they aren't that fast even when they run. On the other hand, here's a very simple algorithm. It's basically what a statistician would call iterative screening regression. You do all univariate regressions, you select the significant coefficients, the ones that are significant you add to your current model, you then do a least squares regression on the current model and figure out the predictions arising from that, take residuals, then do univariate regression again, and then add any new terms that get significant and so on. So that would be, so here's an example. We do univariate regressions and plot the regression coefficients here. Apply a significance test, which gives us a hard threshold such that small coefficients are set to 0. Our first iteration model looks like this. Those are the things that we generate. Then at the next iteration, the regression coefficient on the residual is much smaller because we removed energy from the signal. We apply thresholding. We get a new solution, et cetera, et cetera. We continue. So this iteration you just do a few times. It's not something you tend to limit, but you just do a fixed number of times. If we only did it once, it's just screening regression. If we do it multiple times, it's iterated screening regression. But we're applying an idea that's old to statisticians here in a setting where there's no true noise. And the point of that is to show even with no true noise, all the statistical phenomena are relevant. So the thresholding is actually chosen by the idea that we borrow notions from mathematical statistics and we pretend that all those regression coefficients, a bunch of them are just noise and a few of them are true non-zeros. And then we use sort of ideas out of statistics of how to threshold noise like that. Assuming that it's exactly Gaussian, and again, there's no noise in the problem, but there is randomness in the matrix A. Now, the deal is when I have not correctly recovered my what model to use, then I've left terms out, so there's missed detections. Those missed detections cause cross-channel interference. Every missed detection causes one of the other coefficients somewhere to be disturbed. The net impact of all that cross-channel interference is Gaussian. And here you see it at the first iteration, and we're using different matrix ensembles like random projections, Bernoulli ensemble, or Gaussian ensemble. There's this cross-channel interference from the terms you haven't discovered yet. They disturb all the coefficients, and that's where the Gaussian is coming from. It's the fact that at any given stage you only have a partial model, and even though there's no noise in the problem, the things not yet discovered give a pseudo noise. The phase transitions that you have for two different thresholding schemes can be observed for this. So again, with the same kind of diagram that we've been having, you can observe the empirical results that up to some critical level, you don't make any mistakes, and then after that, you start making mistakes. And this algorithm is obviously a bit more erratic than that one. This is based on false discovery rate, and this is based on the false alarm rate. Thresholding that would be familiar to statisticians. The curves that are here are calculated theoretically. They're not the same as the curves we've been putting up before, and they derive from considerations which are appropriate to this algorithm. But you can calculate a theoretical curve and get an empirical match. And the way you do it is you again use this triangular ray setting, and you measure the operating characteristics of the thresholding at each stage. So how many misdetections and false alarms there'll be, and out of that you can derive everything that you need. The underlying thing that's going on is that the cross-channel interference that you have at each stage obeys a kind of limit theorem. Well, obeys a limit theorem of a kind of interesting form, which is that the cross-channel interference at the different stages of the algorithm behaves exactly like a random walk. except that there's a conditioning in such a way that the only coefficients that you're looking at a given stage are those which didn't pass threshold before. And so it's like you're looking at random walk that didn't cross a barrier before. This is for coefficients that have not been selected at any stage. Once something's selected, it's taken out of the game. So obviously cross-channel interference doesn't have that property in those once you get in the model. Okay, so what are the insights? Here, there's no noise in the problem, but having an underdetermined system is not as catastrophic as you might think. What it actually does is add noise. Like indeterminacy is the same as adding noise. This noise is a pseudo-noise. It's a cross-channel interference. And if you have random matrices from the ensembles we've been talking about, it has a Gaussian distribution. There's a good phase and a bad phase, and in the good phase you can drive the thing to zero iteratively. In the bad phase, it'll stay large. Now, the fact that you have this phase transition behavior and that it's pretty good even compared to L1 is quite interesting because there's a fixed number of linear algebraic operations being done. There's essentially the total work in the algorithm is essentially 10 multiplications by A and 10 multiplications by A transpose, and that's the whole thing. So, and it takes like a minute to program. So it works pretty well in that setting. So now I'd like to connect back with sparse linear modeling. So back to something that statisticians appreciate. This slide has been up before. It's just all the same. We're changing back notation. We now, again, we have underdetermined systems implicitly, but we're using standard statistical terms. So capital A becomes capital X, and little x0 becomes beta, and so on. So we saw this diagram before. And I mentioned the problem of are phase transitions inevitable? That is to say, are the phase transitions that we're seeing for algorithms just because we don't know the right algorithm yet, or is there some intrinsic thing about the problem which says there must be these phase transitions, or at least some level of phase transition has to happen? Okay, so if we use this triangular array setting and we make an assumption on Bayes risk, which is called replica symmetry by statistical physicists, then conditional on that assumption, we have the following result. There's a particular function, which is going to be described later, that will show how to calculate, such that if you're in the domain of the parameters that's above that boundary curve, the minimax risk is unbounded. And so you just, in the standard way that frequentist statisticians would look at it, is like, don't go there. You can't do this problem. You really can't. Doesn't matter what algorithm, there's no measurable function of the data that's going to get you anywhere. And this is quite interesting because sigma squared here is in some sense, the predictive risk, you would think, and yet this is even worse. Okay. Now the function can be precisely characterized. It has the following asymptotic as delta goes to 0. And obviously this matches with the asymptotic that Jared and I derived in polytope theory in the noiseless case. So this is saying that what you see in the noiseless case for L1, you see in the noisy case for everything. Okay, what are the ingredients of this? Well, you need to know about three things. First of all, minimax estimation in the sparse normal mean problem, a kind of now classical topic. Bayes risk calculation using spin glasses, and something I really don't have time to discuss at the moment is the replica symmetry assumption or use of cavity method. What is sparse normal mean problem? Here we have scalars. We have a parameter theta which may or may not be 0. It's usually 0. And the minimax risk is to min over all rules, the max over all theta. What I should say here is the max over all laws of theta that obey this constraint, that risk. This was discussed by Peter Bickel in the early 1980s in sort of a Lagrangian dual form, and Ian Johnson and I did a fair amount of work on this later. The solution goes as follows. If we define the scalar Bayes risk when theta has a known law, then the least favorable is the largest that this can be. And the asymptotics of the least favorable risk one can work out. And the actual worst case prior that causes the least favorable risk one can work out. It's a 3-point prior, which puts mass at 0, of course, by constraint, and at 2 other points that can be characterized precisely. Okay, so intuitively what this is saying is if I have to estimate a single scalar parameter, which may be 0, maybe not, then what I ought to do is pretend that if it's not 0, it's maybe at plus or minus √2 log epsilon inverse times the noise level. So depending on my attitude about the sparsity or how likely it is to be non-zero, I would change exactly where to be planning for a non-zero. So the Bayes risk calculation is based on this setup. We assume a linear model with a certain number of non-zeros in beta according to binomial. We assume a Bayesian prior on the non-zero sites, and we look at things in dimension normalized quadratic loss. So what's the Bayes risk? There's a trick out of the theory of spin glasses which lets you evaluate the Bayes risk using using a heuristic or an assumption called replica symmetry. And if you work it all out, I mean, if you work it out and then kind of work real hard to re-express it in an intelligent form, you work it out in the way that it's written in a spin glass text or something, you won't understand it this way at all. You look for the fixed point of this relation and call that tau, and then the replica symmetric solution for the Bayes risk is exactly this number. So it's the Bayes risk at a certain level of epsilon, which is the fraction of non-zeros, and at a certain level of noise with that underlying assumption f. So that's for one particular f, letting n go to infinity with f fixed. Then if we maximize over f and put in the least favorable, well, because we know the least favorable for expressions of this kind when this is fixed and that's fixed, you can kind of guess that you just have to plug in the least favorable in the obvious way. So what we see is that the Bayes risk for the sparse model selection problem is formally the same as the Bayes risk in the sparse normal means problem. With these substitutions, the noise level is increased from the per parameter nominal noise level to add an extra term. And the sparsity parameter in the normal means problem is, of course, the right thing calibrated to the problem. This extra noise here is self-induced and self-consistent because of the fixed point relation. So again, we see in this problem that having p bigger than n just means that you're adding extra noise. Indeterminacy, it just means you have a noisier problem. However, the noise is determined implicitly. It's not you're adding noise of a fixed amount from outside. It's a self-induced extra noise. There's a technique called cavity method which lets you understand what this is in a heuristic way, which would be the way to prove it is to go through this kind of analysis. If we did ordinary univariate regression, we would get the true beta that we're interested in, plus some disturbing noise, plus cross-channel interference. That is, take the prediction from all other coordinates, push it through the predictor matrix there, and then see what the influence is on this coordinate. That's cross-channel interference. Now, if we put in the Bayes estimate on all other coordinates, subtract it out, then what we're going to get is an expression like this for what's called in applied text, this is the adjusted variables plot. It's a mono-regression coefficient adjusted for the influence of the other variables. And if you make the guess that this basically has nothing to do with the jth coordinate and superposes as a Gaussian variable, then you would get this. And that is exactly consistent with the model that, with the replica theory result, that namely there's this extra term here of additional noise, which is caused by the cross-channel interference. Okay, in any event, if we kind of press on with the analysis, we can see where this breakdown point comes from. So we have this fixed point relation that the additional noise that's caused by cross-channel interference is going to obey this fixed point. If we chose the least favorable prior, then we have an expression for this, that m star epsilon that I wrote. So we re-express this, we get an expression with nothing but m star epsilon on one side and delta and tau's on the other side. If we then rearrange, if we take that display and rearrange it a little bit and then use the asymptotic for this, we get the result that we were talking about, that namely what's going to happen is this self-induced noise is going to blow up at a certain point where 1 is equal to this ratio. And through the asymptotics for the risk of the least favorable prior, we get that it blows up at that point. Okay, so the insights that you get from this kind of analysis is that, again, having more unknowns than you know what to do with is equivalent to a determined problem with added noise, but only up to the point where you have a breakdown, and that has to happen at this point. Now, what's actually been done here is a conditional result, because we're assuming replica symmetry, and you know that your attitude towards that depends on your field. So it's been considered a standard thing to do in statistical physics for a long time. In information theory, it's now considered that you can just publish a result and not even mention it and call it a theorem, even though there's an assumption of replica symmetry embedded in there. I can point you articles and page numbers and so on to show that that became the reigning assumption in information theory. If you're someone like Talleyrand, then you think you have to use the cavity method and prove every step. And I've outlined what the cavity method analysis is here. Okay, conclusions. In the modern world, we often expect a situation where there's a small number of true predictors, many potential, we don't know which ones, and a limited number of observations in such a way that we're in this zone. For algorithms, we often see phase transitions, and this phase transition, which Jared and I found in the noiseless case, also seems to infect all methods of model selection in the noisy case. It says when the number of observations about 2 times the log of the number of potential predictors over actual predictors times the number of actual predictors, things blow up. And again, there's this kind of underlying motif under many of these things that you're essentially adding noise with the Gaussian distribution, which comes out of using the random matrices. To explain some of the phenomena we've talked about would require going to some quite deeper issues, since we have a fairly general audience, although there are many specialists here perhaps who know even more about these topics than I do. I've only been able to indicate that developments in these areas would all have influences on the topics of this workshop. And let's see, so just to sum up, I think that a lot of research is being done and can be done using some of the high-dimensional geometric insights that somehow involve these topics, and perhaps we'll see more development during the whole program here at the Newton Institute. Thank you very much.
Time for a couple of questions.
To what extent, I mean, the Gaussian is clearly sort of coming out of the geometry on that part, but in the statistical formulation, the Gaussian is sort of coming in through the error, it's coming in through the model. If you don't have Gaussian in the statistical formulation, does the form of the curve change? You no longer have.
Oh, okay. So there's several. You raised a couple of good issues. So we get. Right. So using a random matrix for the predictor matrix gives you this Gaussian effect because the missed detections then have a Gaussian influence on all coefficients in any regression that you're doing on a residual, so to speak. Then if you add, then in addition there's statistical noise that's added into the predictors. You could imagine that either the matrix has weird things that creates non-Gaussian phenomena, or that the statistics have outliers and other related things. The statistics of the statistical noise are heavy-tailed and so on. I'm guessing that if you really knew that there were heavy-tailed noise distributions and you used an appropriate robust estimator, then when you look at the normal equations and so on, you'll kind of be back to this situation. That is, you'll have, as you well know from all your work on robust linear models, you'll get Gaussian asymptotic distributions for the coefficients, even though you have non-Gaussian errors. And that's because you put in, say, a score function with bounded influence. I suspect, But if I just used something with L2, then penalize it, then I think you get leakage, of the non-Gaussian stuff in the noise over into the coefficients, and then these phenomena would be quite different. Did I help there?
I think so. The thing, I guess one of the things that also made me think of it is because, of course, the form, the two log stuff, right? That comes up in Gaussian extreme value theory, as you well,
exactly.
as you well know. So I was wondering if that somehow, because of course, if you don't have Gaussians, then the extreme value behavior can be quite different.
Right. So I'll agree with you. If you used, if the z term in the linear model is really non-Gaussian, and you don't change your likelihood to a robustified likelihood, I agree with you that all of this will change.
So in this convex polytopes discussion, it's completely basis dependent, isn't it? So, but maybe your small number P of predictors would depend on taking some linear combination of the predictors given natural.
Oh yeah, that's a very good point. So, what we're sort of assuming is that you've chosen a basis in the space of predictors in such a way that a small number of terms in that basis is what matters. So, here's an example. Okay, let's say by imaging, I get 1 million observations of your face, and I want to predict something, right? So that's an extremely bad basis because each pixel tells me almost nothing. But maybe I have a basis that's a better basis in which there's only a small number of coefficients that really matter. And so people in harmonic analysis have developed bases of that kind. So there's wavelets and many other things that have been developed which do sparsify the image content quite a bit. So I'm sort of assuming you adopt a coordinate system to begin with in such a way that in that coordinate system the vector is sparse.
So you have to do some sort of preliminary analysis to decide on what basis to use.
That's often the case, yes, I would agree.
Have you looked at the problem where you have a sparse matrix and on the right-hand side of a vector y, which is not the correct one, and you still try to solve it, what is then the sparsest solution?
I'm sorry, the matrix itself is sparse. 'Cause
No. You have your problem ax equals y, which you discussed, but
Oh yeah, I mean I should say, you know, there are dozens of people working on this stuff, and probably half a dozen in the room right now, and I'm just touching on some corner of the whole thing. So definitely, this has all been, you know, very carefully looked at by a number of authors. So what happens if it's only approximately sparse? So y equals ax0 plus residual, right? That's what you're saying?
I'm saying you don't have the correct y, you have a wrong y, and you still try to find a sparse solution.
Oh,
How
yeah.
sparse can you get?
Right. I mean, people have, there's extensive literature on that, and we you know, there's questions of if you're a small perturbation away from a vector that's sparsely representable, does the reconstruction by, say, penalized L1 approximate the sparsest representation that you know exists, right? And there are results of that form, and they all have, again, the character that below a sparsity threshold something works, and above a sparsity threshold something doesn't work. And, you know, I mean, there's many results. So as an example, Emmanuel Condes is in the back of the audience. You could ask him about his results on that, and, you know, several other people have worked on those problems.
That will be the last one.
You spoke about the L1 versus L0 minimization problem, right? So I'm not sure I understood where is the boundary between the region where the two solutions coincide and what they don't. Whether it's the same boundary as the 2k log of n over p, or is it somewhere else in the graph? Where would it sit in comparison?
Oh, okay. So that asymptotic result is what happens at the extreme right end. So there's, you know, at any finite value of delta, there's just a phase transition at the place wherever it is, but the asymptotic behavior of that is, you know, 2 log 1 over, whatever it is, 2 log 1
so
over
where is
delta.
the boundary between the L1 and L0 solutions coinciding and not coinciding?
Yeah. And it's not just that they don't coincide, but they're like dramatically different after that. So the sparsest thing, like you put in something sparse, you get out something totally dense once you cross there.
So we now have a coffee break, I guess till about 11:35. Coffee is outside. If you're interested in going to the conference center and have not yet signed up for it, this little leaflet suggests that you do this before 12 o'clock today. Otherwise, it's means now, basically. And at lunchtime, one of the most convenient ways of having lunch is to have lunch in Wilson Court. Not everybody will automatically be eligible for that. If you're not, then you have to get a dining card, which means going to the Porter's Lodge and paying money. And I'm told that some of you might want to do that during the coffee break, because then you don't have to queue up